Testing, testing, 1, 2, 3. Hello, hello. Okay. All right. Hi, everyone. Thanks for coming out. My name is Daniel Shora-Salgado. I'm with FHWA, and I'll be moderating this section. I saw someone yawn just now. That must have been from the Scour session you just came from. Don't worry. This session will be much, much more exciting. We like coastal. Coastal's fun. So we're going to have 4 presentations. First and second up is going to be Bret Webb. Unfortunately, his colleague Bo Buring was not able to make it today, but Bret's covering for him. So quick bio for Bret. Dr. Bret Webb is a professor of coastal engineering at the University of South Alabama and senior coastal engineer and vice president of South Coast Engineers. Bret is a licensed professional engineer and a board-certified coastal engineer. Bret's research and consulting focus on coastal resilience, specifically resilience of the built and natural environments to extreme events and sea level rise. With that, I'll welcome Bret up.
Thanks, Daniel. So I apologize in advance for my appearance. I don't normally wear the short pants to conference presentations, but they've had me a little busy over doing flume demos in the Georgia Tech lab this week, and I did not have a chance to change before I came here. So my apologies. As Roger said earlier, I look comfortable, but I'm a little uncomfortable being comfortable. So just bear with me. But you know, one of my full-time jobs is I am a professor, so I can kind of get away with this stuff. We're going to talk about, in the first and the second presentations, so you're kind of stuck with me for a while, I apologize, kind of guidance development work that we've been assisting federal highways with over the past 5 to 6 years. And really the work that my business partner and colleague, Dr. Scott Douglas, and I have been providing for FHWA really over the past 15 years is helping them develop guidance for transportation professionals that have to deal with the planning, design, operation, and maintenance of coastal highways. And we're going to use the term coastal highways kind of loosely, and it's really an all-encompassing term that captures roads, bridges, tunnels, and all of the associated infrastructure that goes along with transportation systems. So it's drainage and everything else that goes along with it. The first presentation is really going to be kind of an overview or an introduction to our implementation guide for nature-based solutions that can improve or enhance the resilience of coastal transportation infrastructure. And there's a statement that I must put up here first. And while you're reading this statement about this is not FHWA's fault for everything I'm about to say, these are their slides. These were developed as part of the outreach materials at the end of the project delivery cycle with the entire team. And this is the point at which, while you're reading this, I will acknowledge the great work of all of our contributors on our team. This was primed by ICF International, and so Brenda Dix and Susan Assam, were ICF, basically our project managers and leaders on that project. And then we had South Coast Engineers kind of doing some of the technical work. But it was totally a team effort, and this was led by Tina Hodges while she was still with USDOT at the time, along with Becky Lupus, Rob Kaflanos, and all of the usual suspects. If there was an origin story for nature-based solutions in the U.S. Department of Transportation in the coastal environment, this is it. So it's this language that popped up in the strategic plan that said DOT will increase its effectiveness in ensuring that infrastructure is resilient enough to withstand extreme weather. Now this at the time was kind of code for extreme meant not only extreme conditions but a lot of other stuff like climate change and sea level rise and changing ocean conditions. And really, it really kind of kicked off a wave of pilot studies that were done across the United States that had geographic diversity, diversity of the infrastructure type or asset type, and also diversity in the resilience needs that DOTs really were looking for across the country. So this really led into the nature-based solutions for coastal highway resilience development cycle. In a precursor to developing the guide, there were 5 pilot projects around the country that were funded by USDOT Federal Highway Administration. They were carried out by Oregon DOT, a joint study by Maine and New Hampshire DOTs. One that I participated with, which Mandy Gong is in the audience, Mississippi DOT, she was my project manager at the time, Delaware DOT, and then U.S. Army Corps of Engineers in New Jersey. After the pilot projects had been conducted, wrapped up, finalized, reported, delivered, that's when the next phase of the development cycle started, and it really kicked off with developing and writing a white paper about nature-based solutions, and really within the context of the transportation setting. So getting the transportation professional to understand, like marry their knowledge of hydraulic design, transportation planning, transportation maintenance, and put that into the context of nature-based solutions. That was used to inform a series of regional peer exchanges that included both nature-based solutions professionals, transportation professionals, environmental professionals, regulatory professionals, funding professionals, all encompassing peer exchanges. The white paper was used as sort of the setup to start that conversation, to figure out what the most common hurdles were going to be. What are the stumbling blocks? Where do we find the funding? How do we do the design? How do we get them through the regulatory process? How do we incorporate them into project delivery cycles? And this really kind of culminated in a peer exchange report, which then fed in a bunch of really useful information into the development of the guide itself. And it got us in the development team really intimately familiar with the struggles that the DOT professionals were going to face when trying to plan, design, implement, and maintain nature-based solutions, kind of working without a safety net in a world where a lot of their staff does not have this expertise. The culmination of that was the implementation guide itself, which was published in 2019. And we're going to give a brief overview of that. And it includes technical fact sheets that provide some examples. You know, it's not every example, but just some of nature-based solutions that might be appropriate for improving the resilience of coastal highways. Talks about their benefits and typical costs, so it kind of puts them kind of on equal footing with what we're doing today, kind of business as usual armoring and resilience and stabilization approaches to get people to understand that we're not really talking about increasing the cost of what we're doing. We might be talking about increasing the time to implementation because the regulatory process is a little bit different, it takes more time. But fundamentally designing that infrastructure really is at an equivalent cost. And then talk about implementation considerations. So when we say nature-based solutions, we are adopting this definition, which has kind of been cobbled together from a bunch of different agency definitions on this topic. And it's probably more closely aligned with definitions that you would find in the U.S. Army Corps of Engineers or NOAA. But really, we took the stance of this is the use of natural materials and processes as alternatives to or ecological enhancements of traditional shoreline stabilization and infrastructure protection techniques. Now, the U.S. DOT actually, before they got into coastal nature-based solutions, it really kind of had a lot of experience with green infrastructure and more like stream restoration projects and things like that in the inland side. And they've got that expertise. They just kind of need to translate it down to the coast. So they're not necessarily all that unfamiliar with that type of language. Some of the technical fact sheets, they contain a lot more information than just pictures, but they're kind of two-sided and set up in kind of a graphical format. They're nice and glossy. You can pull them out of the guide and put them in front of a funder or a regulator or the public and get them to kind of easily understand what it is you're talking about. And some examples might include kind of the preservation or enhancement or protection of an intertidal marsh that might already be protecting or providing some level of shoreline stabilization for a road along a bay or an estuary or a sound. Maybe something like dune restoration. Maybe you've got existing dunes that have been depleted through storms, and those dunes are sacrificial volumes of sand that are really meant to kind of delay the onset of flooding, but also really kind of shield the upland infrastructure from direct wave attack, at least for some period of time during the storm. So replacing those dunes and vegetating those dunes. And then even going to something like an intentionally engineered beach design where it's trapped in between artificial headland structures, and this is called a pocket beach design, that we've actually seen at least one DOT in the United States use this approach very effectively to actually improve their infrastructure resilience along the York River, which is a tributary to Chesapeake Bay. Well, within the full suite of resilient strategies and this kind of integrated approach, you can think of like boiling this down to like three different boxes on the screen. And one is really the thing that we've been doing fairly well up to this point, which is the structural solutions. So this is just the engineered conventional way of making our infrastructure more resilient. Bottom line, it's really focused more on hardening than adapting. So resist the stress or resist the force. The other kind of category is the policy or the non-structural options or solutions. So this could be planning and zoning changes, land use changes, different flood zone regulations, so that's kind of proactive or there are reactive strategies where maybe you've got an area that floods regularly, and so it's all about signage and detouring and things like that. But there's this other category, which is the nature-based solution, which is really all-encompassing and captures natural features, the nature-based features, which are kind of like natural systems, but they've been designed and engineered and implemented by humans, and also hybrid approaches, which are logic combinations not only of natural nature-based features, but those in conjunction, perhaps working in tandem with our conventional engineered solutions that provide that kind of extreme event protection. The guide starts off really after the technical fact sheets with a chapter on benefits and costs. So in the peer exchanges, the DOT professional said, you've got to give us this information up front, because if we want to do something that's different than what we're doing today, we're going to have to take that to a supervisor or to the regulatory agency or to a funder and get them to understand what we're talking about and why this is better, not just different, but better than what we're doing today. So we put that up front in that kind of introductory chapter. And really describes the benefits not only in terms of the ecological benefits in nature-based solutions, but also the direct hazard reduction benefits that they provide up to a certain point. So we intentionally try not to do a lot of greenwashing in the guide, because there is a point at which the nature-based infrastructure really doesn't provide any level of protection that's beneficial to the upland infrastructure. And that's really when it gets submerged and overtopped during these really extreme events. But really it's meant more for managing the day-to-day stresses, the cumulative stresses that build up over time, that erode shorelines, that frequently flood and inundate roadways and bridge approaches. These are the places where nature-based infrastructure really shine. It also talks about benefits in terms of overall benefits to recreation and tourism and just overall aesthetics and public perception and kind of willingness to engage with these natural and nature-based features. But then the other big thing is cost. So we've got tabulated costs for typical nature-based solutions and typical conventional engineering solutions, and they're pretty much on even footing. We don't see big disparities either way. We also talk about who's required for success in these types of projects, and we kind of put them into three groups. So first and foremost, if we're dealing with transportation systems, the transportation professionals are a part of this process from beginning to end. The coastal engineers and coastal ecologists or wetland biologists or wildlife ecologists, or whoever it is that has the expertise that's appropriate or most germane to what your, the ecological setting or geological setting that you're working in, they need to be a part of that project. And really you could add a fourth circle here too, the regulatory professionals, and engaging them early on in the process to get them on board so they understand what you're trying to do. The other important thing is understanding that DOT's staffing generally does not have all the expertise that's required to fill all those three circles. They can certainly get one of them, but maybe not always the other two or three or four or however many that you need. That's where developing strategic partnerships with a lot of agencies that have icons or logos on the screen becomes very important, because these are this is your community of practice for the agencies and the staff and the professionals that are doing this type of nature-based work. And not only do they have the expertise to help you in the planning, design, and implementation and maintenance and monitoring of these projects, a lot of these people also offer funding for you to actually implement these projects that are outside of your normal pools of funding from transportation agencies. It also helps you on the regulatory side. They've got the knowledge and the expertise that your staff might need to actually help walk this project design through the regulatory process to get that all required permit at the end. Then the rest of the chapters in the guide are set up to mirror a typical transportation project delivery cycle or process. So next step, planning and funding. So how do we plan to implement nature-based solutions, and where does the funding come from to actually design and implement those features? We really focus on trying to incorporate nature-based solutions into long-range transportation planning, specifically early in the process, for a couple of reasons. Number one, it can probably help you address some of your resilience needs long-term, but it could also maybe address some of your ecological needs. So if you've got a big, long project that you're trying to mobilize that is going to have impacts in ecologically sensitive areas, there are opportunities to intentionally use the nature-based solutions to get you mitigation credits for those impacts that you're going to have. And so if you thoughtfully, intentionally incorporate this early into the project delivery process, the better chance you're going to have in actually realizing those goals. and also allows you to incorporate ecosystem thought and process into the transportation delivering cycle. And the best way to do that is really FHWA's ecological framework. So this is this 10-step or 9-step process for actually ecosystem-based planning, where you develop a regional ecosystem framework, you see how your long-range transportation planning or corridor fits into that framework, you design or describe or plan for things that can be incorporated into that delivery process to mitigate impacts or improve the overall ecological function or resilience function of your infrastructure, and that all gets wrapped up into this ecosystem-based approach to transportation planning. If you're not aware of it, go to the Ecological Framework website. They've got lots of great materials that you can download and kind of educate yourself on what it is, how it works, how it's applied. Where does the funding come from these projects? It's not just from transportation agencies. There's a big pot of money from lots of different agencies that help facilitate implementation of these types of projects. Number one, coastal restoration agencies. So National Fish and Wildlife Federation, they're funding lots of ecosystem, nature-based approaches for the enhancement and restoration and protection of critically sensitive habitats around the country. There's also FEMA for their hazard mitigation grants. These types of projects qualify for those pots of funding. So it's not just taking money away from a project, it's actually supplementing your project with new streams of funding that you probably haven't had access to before. Next chapter goes into assessment, and it's called site assessment, but it's really assessment of your site characteristics, but also assessment of your resilience needs. So are you trying to prevent flooding? Are you trying to prevent erosion? Are you trying to prevent wave run-up and overtopping and flooding of a roadway? Are you trying to protect a bridge? Are you trying to protect a tunnel entrance? What are you trying to achieve by implementing this nature-based solution, both in terms of the resilience needs and the ecological benefits? And so we walk the reader through kind of this framework of assessing the site conditions, assessing the resilience needs, and then kind of marrying those two together and figuring out, okay, what's appropriate in the big suite of options and alternatives, what's appropriate for me to consider before I start ruling stuff out. We then get into design considerations. Now, there's no playbook for designing nature-based solutions right now. There's no reference manual. There's no ASCE7 where you just say, open it up. There's a design equation for a nature-based solution. It's much more abstract than that, which makes engineers generally very uncomfortable, rightfully so. So we give a lot of illustrative lessons learned and design considerations. We also step through and talk about some case studies that are geographically diverse and nature-based diverse, and look at those designs and talk about why they were implemented the way they were, what they were seeking to address, their goals and objectives, how they've been implemented, and how they've performed over time. Because that's kind of the big thing that is typically off-putting for a lot of people, is they think that nature-based solutions is some new thing. It's been around for centuries. We just gave it a name. This is often the way that we have been doing shoreline stabilization, ecosystem restoration, and enhancement for years. Somebody just put a fancy name on it. That's all that's happened. One case study that we give is Alabama DOT is replacing a bridge, and as a result, they're going to have a realignment, horizontal alignment of the approach, and it's going to have to fill some water bottoms in Mobile Bay. And in doing so, they're going to fill over some existing submerged aquatic vegetation, which is, if you all work in coastal states and you're impacting SAVs, that's no-no lands. So we're getting into major mitigation problems. So this actually happened during the delivery cycle of implementing or developing the guide. And so TINA at the time got us together with Alabama DOT, and they said, hey, let's work together on a conceptual alternative to what you were proposing, which is just filling in all the water bottoms and putting in a revetment or a seawall. And let's think about a nature-based solution, kind of a hybrid approach that would give the DOT what they need for extreme event protection, but also maybe mitigate the impacts to the SAVs that would be filled over top of. So this is the existing condition. There's just this vertical seawall along the bay. It's very shallow at the base, and generally the bay is shallow. It's only a few feet deep in most places. And it supports lots of different types of vegetation, both submerged and emergent marsh. And one of the things that's been lost more than any type of other vegetative group within Mobile Bay, due to the construction of a causeway across the bay about a century ago, is it's really cut off progradation of the river deltas, and it's really cut off expansion of the intertidal marsh in the ecosystem. So what we came up with and what we suggested after about 8 or 9 different alternative combinations that we put in front of DOT. They landed on this one as being the most palatable. And what it is it's a hybrid revetment where there's a revetment up high and a marsh down low. It's kind of like the mullet hairstyle. It's like, business in the front, party in the back. So this one is like business up top and party down low. Party for the crabs and the critters and the fish and, everything that likes the intertidal marsh. And because the bay is very large, there's a lot of fetch. That's the distance that wind can blow across the body of the water to generate waves. And this shoreline in alignment faces to the south and the longest axis of the bay. So when we have a south wind, the bay really gets rocking and rolling. We've got really big waves that are hitting this embankment. So we do need some protection there to reduce the wave energy so we can have an intertidal marsh. So we've got these little artificial headland structures out there, what we call basically detached, segmented offshore breakwaters. They're fairly small, and they intentionally have gaps in between them to allow ingress and egress, not only for tidal flow and circulation, but also for all the little critters that want to get in and out of the marsh. Now, this doesn't look very fascinating in plan form, but if we look at it in profile, we can kind of drive home the benefits of having kind of the hybrid revetment. So if we're looking in the cross section, here's the roadway alignment in here, and up high, this is, by the way, a distorted scale. So there's a lot of horizontal and not a lot of vertical here. Here's the upper part of the revetment, here's the intertidal marsh, and here's your offshore little segmented breakwater. But what you've done is you've removed all of this revetment stone down here that is really not needed most of the time because all of the wave action is up here on the upper part of the revetment. So that revetment stone at the bottom, all it is stabilization for everything above it. So what if we just bury that, got rid of it, and the balance of that stone that we remove actually is perfectly balanced by the amount of stone that we need out there. So it's really, the only additional cost is bringing in this fill material and putting plants in there, which is not altogether all that expensive, and it's way less expensive than mitigating their impacts to SAV. There are also other examples from different parts of the country. So I tend to be a little biased on the Gulf Coast, and anybody that reads our documentation, it kind of is a little Gulf Coast heavy, and that's, not by coincidence. But we did grab case studies from all around the country. This one's from New Hampshire. So now instead of just a couple feet tide range, we're dealing with a big swing in the tide, which would create some problems for thinking about stabilizing and enhancing this embankment. And so if we look at this in cross section, what they've got is kind of a stepped revetment, where they've got different terraces with planting, vegetative plantings at the different terraces that are appropriate for those tidal stages. So it's going to get kind of a continuum of vegetation all the way from the highest stages down to the lowest stages of water through those tidal swings. Oregon, in their pilot project, they look at this eroding bluff on the Oregon coast, and you stand at the base of this thing and look up. It's this massive problem that seems intractable, and they came up with a really interesting nature-based solution, which was essentially a vegetated terrace approach, and it's kind of an MSE, mechanically stabilized earth wall system that has vegetation on it, but then they've got this cobble berm and beach system down at the base, which is reflective of the actual material that makes up the beaches at that stretch of the Oregon coast. So that cobble beach actually kind of gets stripped off in the wintertime, the sand's underneath, and then you'll see the cobble back, the sand gets stripped off the cobble during the winter, and then the sand comes up and buries the cobble in the summer again. But generally always has a cobble beach at the toe. And then we move from design and case studies into permitting. So there are 3 general ways that you can step through the permitting process for these types of projects. There's a nationwide project or permit in some states, general programmatic permits or regional permits, and then also the more complicated, all-encompassing individual permit process. And there are benefits and challenges associated with all of those. Then we get into construction, advice, techniques. This is not a standards-based construction specification. So that makes people scary because there's no playbook, there's no design manual, there's no standard by which we design a nature-based solution. So we actually recommend something that AASHTO has already developed guidance for vegetation, which is going to a performance-based contracting mechanism. So you're actually putting to the design engineers and the contractors a performance standard. And as long as they're meeting that performance standard, everybody's happy and everybody gets paid. But if performance is lacking, they have to take corrective measures to go out and meet the performance standard or objective. That kind of takes some of the burden and stress and heat off of the DOTs and might be enough of a sway to get them moving in the right direction. And then we talk about monitoring and the need for adaptive management. So if you're interested in how this is performing, you need to go into it with a goal or objective, and you need to monitor how it's doing. And if it's not performing to your goal or objective, you need to take corrective action. And this can happen in some cases. And then we kind of close off with, a little summary at the end, and kind of the takeaway message is, it's kind of better to work with Mother Nature than to impose our will upon it. And really to kind of be intentional and thoughtful in the development of your nature-based solutions so that they're not just like painted a shade of green, but actually are intentionally kind of green. So for more information, contact Elizabeth Habick at headquarters, and there's a link there to some guidance. If you just do a Google search for USDOT, FHWA, Coastal Green Infrastructure, it will take you to the site. So with that, Daniel, time for questions, or do we need to move on? Yes, sir. I know you.
We're working on one HEC-25 in North Carolina. And honestly, the design of the lake shoreline was probably the easier part. It was all the maintenance of traffic. We had 27,000 vehicles a day that got ran across that causeway. And then the agency, they made us shrink quite a bit due to impacts to existing resources. And so we had a heck of a time. We were sort of losing some of the efficiency of the marsh because the agency just wouldn't fly off.
In most states, it's still true, sad but true, that it is easier to permit a bulkhead, a seawall, or a revetment than it is a nature-based solution. Even though we know, and everybody in the regulatory world knows, that that is the wrong thing to do from a water quality standpoint, from a habitat conservation standpoint. You're kind of working against the fundamental underpinnings of why we have the regulations in the first place. Clean Water Act. We're not really helping that at all. But they're more comfortable with permitting the conventional systems. So you get them out of their comfort zone and you start talking about, well, we're going to plant this intertidal marsh, but to do that, we're going to have to fill on top of existing water bottoms. That's a habitat trade-off. Now you're eliminating all of this benthic habitat and putting a marsh on top when a marsh is not supposed to be there, or maybe it's supposed to be, but it's a habitat trade-off situation. So you have to be very intentional about providing good justifications for everything that you're doing, and why, say, an intertidal marsh habitat is, much better in terms of ecological benefit than it is the existing benthos that's there. That's basically just a bunch of worms and things like that. Project delivery is tricky. So these projects are either built from the land side or built from the water side. Obviously, if you're building from the wet, in the wet or from the water side, it gets a lot more expensive. You've got issues with storm and having to mobilize and remobilize equipment and things like that, so it can get tricky for sure. There's no monopoly version to the regulatory process for nature-based solution where you just buy up everybody's property along the way and get to the end and win the game. And that's why really involving the regulators at the first part of the project is so important, because they can kind of head you off at the pass. If you're proposing to do something that they are never going to permit, you can kind of get that out of the way early in the process and start negotiating, okay, what is acceptable? What can we do here? But generally the habitat trade-off issue is an uncomfortable discussion that you have to get the regulatory professionals on board with. And usually that's going to require the more complicated, longer individual permit process, where it's going to go out for public notice. You're going to have to respond to public comments. You're going to have all sorts of, comment disposition stuff that you have to do after the fact. But that's generally the way to step it through. They feel a little bit more comfortable when you go through the entire permit process instead of just taking the shortcut for the nationwide permit or the programmatic permits. But it's more costly. And it's not something that you can do reactive, right? If you're doing storm response maintenance, you don't have time to wait 9 months or 12 months to get a nature-based permit, right? You're going to go back and you're going to put something on that embankment or protect that road in any way that you can quickly enough to fix the problem so it's safe for the traveling public. This is why incorporating this into long-range planning becomes so important, because you can be thoughtful and intentional about what you're doing. But this is never going to be a reactive strategy. It's got to be proactive and planned. Absolutely not. What I would suggest, though, is that the planners actually get the engineers involved earlier in the long-range planning process. And I know that I'm just sitting up here like spouting like this extra burden, more work, extra burden, more stuff to do. But you don't want the planners to build a mousetrap that is not going to work, that you can never design and deliver. So it's better to get everybody on board early in the process and get them included so they can start eliminating. It's like, reality check, this is not going to work, we can't do that. Or yes, that's a possibility, let's keep it in right now until we eliminate it maybe further down the road. And the other thing is not to be so stuck in a groove and have your blinders on where you're only considering one approach. There's probably about 6 different ways to solve the problem, and they all have different shades of gray in terms of how good or bad they're going to be at accomplishing your goals. But you've got to keep them all in and evaluate them in a quantitative fashion to really get to the best answer at the end. That's going to be the biggest bang for the buck, the best benefit to the ecology, the best benefit for resilience, the best benefit long-term in terms of the life cycle of the asset. So don't kind of throw the baby out with the bathwater early in the process. Like, keep them all in and consider everything until they absolutely have to be eliminated and get to one answer. Carlton.
Did you want to finish? Okay. Now, quick question for you. With all the pilot work that you've seen, have you seen anybody take the costs all the way out? Amortizing everything. And the reason I say that is I know we had some work along Florida where we went to the estuaries and we worked with them, and they gave us letters where it shows like $2.5 million in savings to the habitat and other things that were going to be gained by some of the work that we could do along the coastline and improve it. And so I think if anybody ever took that all the way out and really, showed the numbers in real terms, I think that might get more buy-in.
I think that's what you're going to see kind of, everyone's kind of wrapped around the axle on cost, especially in terms of life cycle cost. And that's important, especially for DOTs, because you have to be able to show that and make that justification up first before you're even allowed to consider it. So I think that's the next logical step, and I know there are people working on it. NOAA's Green Infrastructure Database that you can get to through their data repositories, they have a lot more and different costing information than what we present in the book. And I know we've got lots of examples of nature-based projects that have actually been in, like Chesapeake Bay, they've got projects that they've known about that are almost a century old that were kind of, not at the time, not really intentional nature-based solutions. They were kind of more out of necessity, where you had like a farmer that was trying to protect his agricultural land. And so he actually ended up creating a nature-based solution when he was really just trying to protect his agricultural, investment. But they've been tracked and they've been studied over time. And some of these are a century old and still working very well. Though the upfront costs of nature-based solutions might be on par with the conventional approaches, the maintenance issue does come up a lot. And it's like, okay, well, if they're the same price up front, over the life cycle of that investment, how much more am I going to have to pay to maintain a nature-based solution versus a conventional solution? And really, it's going to be a function of how well you design it the first time and how well you monitor it. And you can actually cut out a lot of costs by having intentional monitoring to really solve and address small problems before they become big problems. But there are other long-term costs associated with nature-based solutions that we tend to kind of just gloss over. But like the full amortization, that's a tricky wicket.
Well, yeah, the reason I say that is first before seagrass. You can do it where you're creating seagrass mitigation, which is almost
tough.
You can't put a cost on that, unfortunately.
Yeah.
We can create more of that with the secondary benefit, because then, like you said, if you're in anticipation, now that becomes a whole different ecology. And then species habitat creation that you can gain from that.
Yep.
There's so much value that you can gain from the overall process. I just don't think we're capturing it well enough to demonstrate to the regulators that, hey, this is what we're going to create.
We're not. And there is a whole field of science now dedicated to, monetizing ecosystem services. And there are professionals that do only that. And you can get access to those professionals. Some big companies have them. And there's literature support. They actually put a unit cost on the value of like an acre of salt marsh habitat, an acre of SAV, an acre of a dune, an acre of a beach, an acre of a cobble shoreline or whatever it is. And so you can get to all these things and you can add those up. And the only thing we really don't know is, do those costs stay constant over time? Do they shrink? Do they grow? Do they expand? How does it change? So I think that's one of the missing links right now and kind of a knowledge gap. But I know there are people working on it. I'm good. I'm just gonna soldier on. I've been talking for 2 days. I do kind of talk for a living, and I will warn you all, it's very dangerous giving a professor a microphone. It's like, if any of you have ever read the story to your children, if you give a mouse a cookie, that the same thing happens. All right, where's the other one? All right, so I kind of apologize in advance. I guess I should have kicked off the session by saying, if you came here to see modeling presentations, there's the door. You can come back in like 2 presentations and listen to Jeff and Chow, and they'll woo you and amaze you with modeling stuff. But we are in the coastal session, so happy to be in this one, but not going to talk about modeling today. Bo, our staff engineer at South Coast Engineers, was geared up to provide this presentation. He unfortunately got sick and decided not to spread the gift of COVID to everybody by coming up here. So he is at home nursing his illness and sent me a slide deck and asked me to give a presentation. And I am somewhat familiar with the subject that I'm about to talk to you about. This is the 3rd edition of HEC-25. Which interestingly enough was completed in the year 2019, has a publication date of the year 2020, but wasn't released until the year 2021. So if we think about the things that we're incorporating into HEC-25 3rd edition, dealing with extreme weather and changing ocean conditions, there was language in the document that was uncomfortable for the current legislative body at the time it was completed. So it kind of sat on a shelf for a little while and hung out until everyone got okay with it, and then like within a few weeks of a new administration, poof, it appeared. So we're going to talk about our updated Coastal Resilience Guide. It's an all-encompassing document for transportation working in the coastal environment. So where we started and where we're at now is really HEC-25 2nd edition was released in 2007. And then we followed that up with Volume 2, Assessing Vulnerability to Extreme Events, in about the year 2014, if memory serves correct. And now we've got the new 3rd edition, which is not simply just, hey, we're going to give you a scope of work and a big budget to just take the 2nd edition of Volume 2, put them together, and here's your 3rd edition. This actually has new stuff in it. So a lot of the material from HEC-25 2nd edition and Volume 2 were kind of meshed and put together into this 3rd edition, but we also have a lot of new stuff that wasn't in either one of them before. So what's new in the guidance document? Remember, this isn't a manual. This isn't a design manual. This isn't prescriptive guidance. These are recommendations. This is potential information that you could apply in your work. 3 recommendations for incorporating future sea level projections into design. If you were in this workshop yesterday morning, you heard me talk about that, so we're going to go through a little bit of it again today. Assessing vulnerability of coastal highways to extreme events, incorporating sea level rise into that extreme event evaluation, and tools for doing that, which include modeling, by the way, so we're not totally without modeling in this presentation. Understanding and assessing increased flooding due to sea level rise, and understanding not only what names it goes by and the problems it will cause, the timeliness of when this will happen, but how to project it into the future for your assets. And then also adaptation strategies for coastal highways, in addition to all the other stuff that was already in both of the 2nd edition and the 2nd volume. So in terms of incorporating relative sea level rise into design, we're really talking about incorporating probabilistic projections of global mean sea level rise into your planning and design. and also vulnerability assessments of your existing infrastructure. And incorporating relative sea level rise modifications from either NOAA that provide projections out in the future, which are more like planning-based scenarios, or scientifically physics and process-based projections of global mean sea level out in the future. HEC-25 3rd edition actually recommends that for most transportation infrastructure, and remember by most we're talking about a majority of, so not everything is a big fancy bridge, not everything is a super expensive road. There's a lot of transportation infrastructure which is just conveyance. A lot of what you deal with in terms of maintenance and replacement are culverts. And so a lot of things in the transportation portfolio might be appropriate to consider at least adopting a minimum floor for sea level rise out to the year 2100 and not going below it. But that minimum is not going to be appropriate for the real fancy bridges that are super expensive, long-lived, and difficult to replace when they are damaged. So we really try and get across the point to the user or the reader that a minimum might be okay for some things, but you might want to consider something higher for long-lived, critical, or sensitive infrastructure. And that's really kind of goes down to recommendation 1, just incorporate something into planning and design. There are so many states right now that are in like this stranglehold of analysis paralysis. There are so many options. There are so many projections. They don't know what to do. They don't know what to choose. They don't have any guidance, prescriptive, statutory, or otherwise, that tells them what to do. So in a vacuum, they do nothing. So right now, just do something. At least incorporate it into the planning and design and consider it. As was talked about in yesterday's workshop, not every consideration or implementation actually requires a design modification. It might just be, okay, what's going to happen if we have the sea level rise? Oh, we're okay. We don't need to do anything. But at least assess it. Figure out what the problem's going to be. Recommendation number 2 related to sea level rise, consider the minimum projection out to the year 2100 for most things, but understand that there's uncertainty in this, and for some infrastructure, the minimum might not be appropriate. But the minimum global mean sea level rise value that we're talking about is about 2 feet of mean sea level rise by the end of the year 2100, but that has to be adjusted for local and regional processes that change the global value, either up or down, depending at your location. And so we go to the process-based projections that are tied to the climate scenarios. So we do this because as climate scenarios are updated and change, you just substitute in the new value by the year 2100 and boom, you have the best available science. So there's nothing arbitrary or uncertain about this process. And the minimum recommendation of 2 feet goes along with the median projection of the mitigated concentration pathway scenario. So if we do something to reduce greenhouse gas emissions and bring down or stabilize temperatures, this is the projection that we're going to have. Median, so 50% chance it could be bigger, 50% chance it could be smaller. Now, for some critical or long-lived infrastructure, the minimum is probably not appropriate. And even for some other infrastructure that might be critical for a different reason, could be evacuation route or whatever it is, or just very expensive and difficult to replace, you might want to consider something higher. So we do give an alternative scenario to try and incorporate and think about the uncertainty of, this small little, tidal creek crossing. You don't need to be super conservative in your estimate of future sea level rise if you have to replace that bridge. But the highway bridge on the right-hand side, you might want to be a little conservative, and that's exactly what they did and why those pilings look so long. And so as the alternative recommendation, we say, for the, unmitigated, unabated concentration pathway scenario where it's just business as usual. We keep doing what we're doing, greenhouse gas emissions continue to rise, temperature continues to go up. We look at the 95th percentile of that global mean sea level rise projection out to year 2100, which ends up being about 4 feet. The reason why we gave this range of 2 feet to 4 feet is because we felt it was a very realistic range that most DOT professionals could at least accept and start to think about. Because if you start putting numbers like 8, 9, 10, 11, 12 feet in front of them, you just get this glazed over look. It's like you're helpless. What are you going to do? Because now we're talking about everything on either side of that bridge is underwater. You might not have anybody living there. You might not need those roads. You might not need that bridge. So we're trying to kind of bring it down to be realistic. And in doing this, we're kind of equally criticized by both groups. The alarmists that say, the sky is falling, it's not going to be 4 feet, it's going to be 12 feet or higher. And the people that don't believe that sea level rise is happening at all, it says, I shouldn't have to do this whatsoever. So this range is not so astronomically large and overwhelming that you just give up initially and say, nope, can't do it. I'm going to walk away, just going to ignore it because we can't do anything about it. Worst case scenario, you incorporate this by the year 2100 or by the end of the service life of your asset, you've bought capacity to handling more extreme events. The same things that we could be doing today to prepare for sea level rise are the same things that we should have already been doing to reduce our exposure to coastal hazards today, like the hurricanes and the nor'easters and all of the things that are happening on a relatively frequent basis. If you increase the elevation of something by 2 or 4 feet, that allows 2 or 4 more feet of flooding or 2 or 4 more feet of a bigger wave or whatever it is. So it's not just sea level rise. It's about being resilient to all of the extreme weather events. We also spend a good deal of time talking about an event that's going to happen at a much lower threshold. Really, sea level rise in the absence of anything extreme going on, you're going to have a lot of nuisance flooding of your low-lying infrastructure. Now, this goes by a lot of different names. There's a litany of them on the slide. We call it in the guide, we call it simply increased flooding due to sea level rise, because that's what it is. That is what is contributing to the increased flooding. All your tidal datums are marching up. Your mean sea level is going up, your mean high water is going up, your mean low water is going up. And so just as a function of normal tides on a sunny day, nothing happening, more and more things will be inundated as those tidal datums creep up with global sea level rise. So we've seen lots of examples around the country. Miami has kind of been the poster child for a while of dealing with nuisance flooding, and they've adapted in many ways. So they've raised streets, they've put in pumps, they've dealt with stormwater issues. Annapolis, Maryland has frequent flooding issues, some parts of Hawaii. All of these stormwater systems are tied to the coast. That's where all the drainage goes. And so as your tailwater condition comes up, it gets to a point where it's above the inlets of your stormwater system. And so all of this sunny day flooding that we see, primarily, it's not just water accumulating in pools from precipitation or rain. It's the stormwater system backing up or the groundwater table rising. So groundwater impacts can be felt due to sea level rise, can be felt 10 times further inland than a surface water conveyance would allow sea level rise to flood a low-lying coastal plain. So groundwater table is also rising as global sea levels rise. And this is translated very far inland. Dave Kriebel, now retired professor from the U.S. Naval Academy, did some excellent work and published some excellent guidance, which we have incorporated into the 3rd edition of HEC-25, that provides some relatively simple methodologies for forecasting your days of inundation due to increased flooding due to sea level rise, or nuisance flooding, sunny day flooding, whatever it is. So the idea is that you essentially look at the distribution of high tide stages that are predicted over a year, and you look at where all of those values fall in terms of elevations. And so as an example, in Annapolis, Maryland, near the Naval Academy, there was this one stretch of road that flooded all the time. Well, when Dave first got to the Naval Academy, he said it maybe flooded once a year. By the time he retired, it flooded once every couple weeks. And so it wasn't that the road was only sinking, and there was subsidence there, but it's really global mean sea level is higher than it was when Dave started working at the Naval Academy. So they did this forecast projection, and that is a semi-diurnal, so 2 tides a day system. So you end up with 720 high tide events throughout the year, more or less, or 730. And if you look at the stage distribution as a function of elevation, you can figure out if your road, say, is at an elevation of 1 foot, you can look at how many days of high tide flooding it would exceed that elevation. You can also then forecast this out by adding in your sea level rise projections and adjusting that mean high water tidal datum or stage, and now you can forecast how many more days you're going to be flooded. So as a result, if like that road elevation I think was 2 feet, so it was flooded under present day scenario something like 2 or 3 times or 5 times a year or something like that. But if you've got a sea level rise scenario of 2 feet, now all of a sudden, if you go to an elevation of 2 feet and read up to that curve, now you're inundated 700 times a year. Woo! Basically, the water's flooded twice a day, almost every day of the year. So this is just the biggest tides of the year. This is almost every single tide. So this is problematic. So the forecasting of these inundation curves is very easy to do when we step you through that process. And then we also kind of look at it in a different a way of actually forecasting this out, not in terms of elevation, but year by year, and when you might see the number of days flooding actually change. We also talk about, in a much more kind of comprehensive fashion, we talk about assessing vulnerability. In the fact that vulnerability is generally thought of as a function of 3 criteria: the exposure of your asset to some kind of extreme event or damaging process, the sensitivity of it, so does it have some side of an inherent capability to withstand something larger than it was designed for? So is it a rigid structure that's going to catastrophically fail, or is it a flexible structure like a rubble mound structure, like a revetment, that can kind of flex and adapt to the changing conditions? And then the third one is the adaptive capacity. Most of our transportation infrastructure does not inherently have its own innate capacity to adapt and change and respond to more extreme events or to rising sea levels. So we look at assessing vulnerability as really kind of some function, maybe not a sum or a product, but some function of considering all 3 of these things for a transportation asset. And we look at kind of, I guess you could call this the older style vulnerability assessment resilience framework, where we actually look through this 5-part assessment framework of how to step through and do a vulnerability assessment for a specific project. And there's a slightly different framework that you might go about or process for doing like a system-wide assessment as opposed to a project level assessment. We talk about doing those assessments with one of 3 levels of effort. So level of effort 1 is essentially just use existing data and resources. This could be take an existing flood hazard map, doing a simple modification to project sea level rise inundation, apply some simple equations to estimate velocities or think about shoreline change, and then think about what your asset might see over time. So this is ready access to everything that you already need for the most part. Level 2 is, and a lot of times level of effort 1 is not going to give you a lot of confidence in your results because it is very simple, but it can be used as a screening tool to immediately kind of screen out the infrastructure that you really don't have to worry about. And you could take that leftover group of the stuff that's potentially problematic and move it to level 2 assessment, which is do some original modeling of your critical coastal processes or hazards with the sea level rise baked into the modeling. So you get all of the nonlinear combinations of the sea level rise and a storm surge and the waves, and this is a perfect segue and setup for what Jeff is going to talk about in the next presentation. And then the third one really, which is also what Jeff's going to talk to, is really it's the full soup to nuts. You do everything. It's the original modeling and a probabilistic framework. So now we're not just picking a storm at random or at will and running it. We're actually baking in all of the statistics into this so we can assess in a risk-based framework. So now you have confidence in the answers that you're getting out. So highest level of effort, but also highest confidence in reliability in your results, in your assessments of vulnerability. We separate this out into 4 regions, and it's really not regional by kind of place, but it's more region by coastal processes and the type of processes that might need to be considered or included in the assessments. So Mid-Atlantic and New England coast are lumped together because the process by which you would assess coastal hazards for those is somewhat similar. Exposure to tropical cyclones, but a lot of exposure to nor'easters that are very damaging and occur more frequently than tropical events. Pacific coast and islands for their exposure to not only tropical events, but also tsunamis. Gulf Coast and South Atlantic coast for their exposure to hurricanes and a much lower exposure or significance of nor'easter type events. And then also the Great Lakes, which are a whole different bailiwick altogether. But they are our unsalted coasts. So those lake systems are big enough to support coastal processes that are very similar to what we deal with at the open ocean coasts. We provide case studies that are diverse in terms of level 1, level 2, level 3, that are also geographically diverse. So Pacific Coast, Gulf Coast, New England Coast. So you get to see each one of those levels spelled out and explained of what they entailed, what they did, and what the outcomes were, and why they pursued that level of effort for that particular assessment. We also have a lot more information in HEC-25 third edition about adaptation strategies. This is not just the conventional strategies, but also incorporating some of those nature-based solutions into it. So we spent a great deal of time focusing on getting the DOT professionals to understand what the damaging wave mechanisms are, or damaging coastal mechanisms. So we're talking about wave attack. This thing that we call the weir flow damage mechanism, which if you haven't seen HEC-25, this is where, in the coastal environment, if you've got a coastal road that's kind of parallel to the coast, as it's flooded, the water flows over the road, and the road actually acts like a broad-crested weir. So you've got kind of a high water condition on one side and a low tailwater on the other. And as the water's flowing over the roadway shoulder, you get a little hydraulic jump as you go transition into supercritical flow, and it starts an erosion process that undermines the edge of pavement and will cause the entire pavement to fail, or can. And so we talk about this weir flow damage mechanism. And oh, by the way, now we also have wave contributions on top of that, which are causing this to be way more complicated. Coastal roads in the area of retreating shorelines, that's a big one. A lot of state DOTs absolutely do not want to be in the beach business. But beaches, generally, beaches and dunes are protecting a lot of our transportation infrastructure. So we hear a lot, like, we're not in the beach building business. Well, you're not in the drainage business or the lighting business or the landscaping business or the lawn mowing business, but this is all stuff that we have to do to maintain and support our transportation infrastructure. So DOT should never bear the brunt and the cost and the implementation burden of beach and dune projects, but they should figure out a way to be on board to facilitate it, right? Because they are going to be the recipient of a lot of damage reduction and hazard reduction from those ecosystems and habitats. We have a lot more information in there about overtopping for roadways and bridge approaches and how to calculate those and what they mean in terms of level of service and level of safety to the traveling public. So what's appropriate threshold of overtopping for a pedestrian or a car or a light truck or a semi or whatever it is. And we have more information in there about tsunami hazards as well. And then a bunch of stuff about adaptations. And talking about the full suite of adaptation and resilience. Thinking about managing and maintaining or making stronger, increasing your redundancy of your system, whether it's a structural system or your transportation network. And then thinking about protection versus accommodation and even abandonment or relocation or retreat. And this is not unheard of in coastal states. We've got lots of segments of roads that have already been abandoned and lost, not just along the Gulf Coast and the Mid-Atlantic coast and the California coast, but also along the Great Lakes at the top of the bluffs that are eroding. So lots of different strategies, and we try and give you a little bit of an introduction to all of them so as not to leave anything out. But obviously there are issues and challenges associated with all of these adaptation strategies that really cannot be understated. So with that, I will close out the presentation. Roughly right on time. So, Daniel, time for questions, or should we move on to Jeff? Yes, sir. So we've got some really interesting adaptation options in HEC-25, some of which make DOT professionals very uncomfortable, because one of their strategies is actually keep the alignment low and allow the road to be buried by sand. Now, this is an additional maintenance cost, right? Because if you have to mobilize, scrapers to go out and take sand off the road, NCDOT knows a little something about that. Those costs for any individual storm don't look as big as replacing the road, am I right? But over time, cumulatively, big maintenance cost. I mean, we're talking, millions of dollars maybe over the course of a storm season to keep scraping sand off the road and put it back on the beach or the dune. So it's not without its challenges. So if you could bury the road in sand, you avoid the weir flow damage mechanism. Protecting the shoulder. So if you've got essentially, instead of just having the asphalt pavement roll off into just loose sandy substrate, have a transition. So go gravel, or go totally reinforced, or do a revetment buried underneath the embankment and tucked up underneath the shoulder of the roadway. We've got a bunch of different cross sections that we show as potential adaptation strategies for mitigating the weir flow damage mechanism in HEC-25. And Florida DOT has actually implemented a couple of those in a stretch of road on Okaloosa Island, which goes in between Fort Walton Beach and Destin. And they've got different varieties based on their different exposures and vulnerabilities that they had in the past. And there's actually a study that we did on that to actually do a complete life cycle cost of that adaptation to show that, I mean, the cost savings was tremendous. The upfront cost, very big for the adaptation, but the life cycle savings over the service life of that asset from not having to repair and replace every storm season adds up very quickly over time. And the multiplier is 3 or 4 even without sea level rise, but it goes from 3 or 4 to 6, 7, or 8 when you consider sea level rise out in the future. So we do have some strategies for that. Jennifer.
That Oklahoma Island project is actually one of the FHWA adaptation pilot projects. So you go to the Resilient website for FHWA.
Yeah, it was transportation engineering approaches for resilience to TECR, transportation engineering approaches to climate resilience, TEACR, TECR. And there's also, on the TECR website, there are 3 coastal studies and a bunch of inland studies, and the 3 coastal studies look at nature-based solution, the weir flow damage mechanism adaptation, and then also bridge retrofits for vulnerability to wave loads.
Why are coastal engineers so cool?
Need I say more? Daniel, I go to the beach and I'm at work. So I actually sent a picture to somebody at work and they saw I was at the beach and they said, "Oh, I'm sorry, I disturbed you, you're on vacation." I was like, "Actually, no, I'm in my office." So I don't know, we are kind of a weird bunch. Coastal engineers are a little weird. They're a little outside the norm, I think, for most kind of traditional hydraulic engineers. We're all dealing with natural systems that are defined loosely by probability, but you're dealing with a natural system, so your best laid plans are often thwarted by some new hydraulic event. We deal with that in the coastal environment just like you all deal with it in the inland environment. So I think we're all a little off our rocker. But yeah, I don't know. It's just different. It's a different form of hydraulics. There you go. That's it.